So, ladies and gentlemen, today we are going to look at the concept of colligative properties. What is colligative properties? Colligative properties are the properties of the solution that depend on the concentration of the substance or amount of the substance that added in a solvent, rather than the identity of the substance. So, in colligative properties, is the properties that try to talk on how much of the solid particles you added in a solvent. Like, for example, how did we get a solution? From our basic knowledge, solid plus solvent will always give us solution. So colligative properties, they are the properties that depend on how much of this solid you added in a solvent to give you a solution. And for example, we have some examples of solid here. We have sodium chloride is a salt, magnesium chloride is a salt, potassium iodide is also a salt. But if you look at these three different examples of salts, they have different chemical composition. So colligative properties doesn't concern on the chemical composition of the solid. Rather, it's just only concentration. It's just only depend on how much of that solid particles is added in a solvent. Like, for example, colligative properties is after, is it how many gram of sodium chloride is added? Is it 1 gram? Is it 2 gram? Is it 5 grams? Is it 10 gram or 10 kilograms? So colligative properties is just they are properties that depend on how much the substance is being added. Is it that you added 5 gram or 2 gram? So colligative properties is just different on that. It doesn't concern whether it is magnesium, is zinc chloride, or any. So it doesn't depend on any kinds of the chemical composition of the solid. Rather, it's just only depend on the concentration. So it's just only depend on the concentration of the substance, and that is colligative properties. So what are the conditions for a particular solution to undergo these colligative properties? Number one, the solution must be dilute solution. The solution must be dilute solution. So colligative properties is applied under dilute solution. So you said dilute solution is a solution that have the concentration of less than or equals to 0.2 molar. That is dilute solution. So colligative properties is applied only on dilute solution. And number two, the solution must be ideal solution. It must be ideal solution. This is the second properties of the solution that colligative properties is applied. So it must be dilute solution, and second, the solution must be ideal, and then third, the thing must be, or the solid must be non-volatile and non-electrolytes. Non-volatile solids and non-electrolytes. Non-electrolytes. So the solid should be non-volatile and non-electrolyte. So these are the three conditions for the solution to operate under colligative property. The solution must be ideal, and the solution must be dilute solution, and then it should be non-volatile. That is, the solid must be non-volatile and non-electrolyte. But in a situation where you have your solids as an electrolyte, so generally it increases colligative properties. So if you are dealing with non-electrolytes, if you are dealing with electrolyte solids, so generally the colligative properties increases. And how does it increase? The more the number of molecules or the more the number of ions associated with a solution, the more the colligative properties. Like, for example, if sodium chloride. So when you have sodium chloride, when you dissolve sodium chloride in a solvent like water, you will have something like sodium ion plus chloride ion. So it means that in this case, the number of ions or the number of molecules increases from 1, because here is 1, but here you have 2, because you have 1 here and you have 1. So 1 plus 1, we have 2. So it means that there is dissociation. Here you have one molecules and is now dissociated to produce two molecules. So you see that in this case, the number of the solid particles increases due to this ionization. And remember that colligative properties increases with an increase in the number of the solid particles, or with an increase in the amount of solid particles. So it means that the number of solid particles here increases from 1 to 2. So that is where colligative properties will be increased. So, and this kind of increase after you dissociate a particular solid particles is applied using what we call Van Hoff factor. Van Hoff factor. So the Van Hoff factor here before the dissociation of sodium chloride is 1. And usually this Van Hoff's constant is denoted or is represented with small letter l. So Van Hoff's factor is 1 before dissociation, and after dissociation is now become 2. So these are some basic concept and explanations of colligative properties. Number 1, what is colligative properties? Is a properties of solution that depend on how much, or that depend on the amount of the solid particles that you dissolve in a solvent. That is first, and then second, this colligative properties doesn't depend on the identity as well as the chemical composition of the solid particles. And then thirdly, for the colligative properties to operate, your solution must be dilute, and then your solution must also be ideal, and then your solid particles must be non-volatile and non-electrolyte. But in a situation where your solid particles is electrolyte, then what you are going to do, you have to look at after you add the solid particles into the solvent, does it dissociate? If it dissociates, then you count the number of the dissociating particles, and the more the number of the dissociating particles, the higher the colligative properties. Like in this case, we have 1 molecule of sodium chloride and it's now dissociated to produce 2 molecules of sodium ions and chloride ion. And this number of this increase in the number of the solid particles after dissociation is represented with what we call Van Hoff's factor. So now we are going to look at the colligative properties. So basically we have 4 colligative properties. We have 4 colligative properties. So we have 4 colligative properties. We have vapor pressure lowering, freezing point depression, boiling point elevation, and then we have osmotic pressure. So we are now going to look at these colligative properties one after the other. So now we are going to start with vapor pressure lowering. So what happens in a vapor pressure lowering? So when you add your non-volatile solutes, into a solvent, it's generally lower the boiling the vapor pressure. So when you now have, let's say you have the container, and this is your closed container. So you have your closed container, and you now add non-volatile solutes. So the vapor pressure Vp will increase. So the more you increase the number of the non-volatile solutes into the closed container, the more the vapor pressure will be decreased. And why is it decreased? This vapor pressure decreases due to increase in the number of the solid particles. So what happens in this vapor pressure lowering? When you add a non-volatile solid, after you add this non-volatile solid, it is now going to occupy a space that was already occupied by the solid. And as a result of that, the number of molecules of the solvent that evaporate before adding the non-volatile solid will be decreased. So before you add water molecules, before you add the solvent before you add the solid into the solvent, the water molecules or the solvent molecules can easily evaporate to form a vapor. But when you add the non-volatile solid occupies some spaces, thereby decreasing the evaporation of the norm of thereby decreasing the evaporation of the number of molecules of the solvent. And as a result of that, the vapor pressure of the solvent will decrease. So that is why here we have vapor pressure lowering of the solvent. So as you are adding the number of solid particles into the solvent, then the vapor pressure will be decreasing, because the more you are adding the solids, the more you are finding the species where, the more you are finding the species up to the point that the number of the molecules of the solvent will be very, very difficult to evaporate. Therefore, forming the vapor pressure will be difficult as a result of that. So that is what you call vapor pressure lowering. And this vapor pressure lowering is expressed by what you call Raoult's. So Raoult's law states that the vapor pressure of a solution is equal to the mole fraction of the solvent times the partial pressure of a pure solvent. So this is the Raoult law. So Raoult law states that the vapor pressure of a solution is equal to the vapor pressure of a pure solvent times mole fraction of the solvent. So this XA stands for the mole fraction of the solvent. So in this theory, you can just say vapor pressure of the solution is equal to the mole fraction of the solvent times partial pressure of the solvent. So this is the formula according to Raoult's law that try to describe the vapor pressure lowering. And then now we are going to look at the mole fraction. How do we calculate mole fraction? So now this is the mole fraction of the solvent. And how did we calculate the mole fraction of the solvent? So remember, from going to the mole fraction of the solvent, let's say your solution is made of sodium chloride plus water and now salt solution. And how are you going to play around this mole fraction? So to play around for this mole fraction, what you are going to do, we are now going to one fraction of the solvent. So our solvent here is water. So we are now going to say the mole fraction of water is equal to the number of moles of water divided by the number of moles of water plus the number of moles of sodium chloride. And as I said, the vapor pressure lowering increases. So in the vapor pressure lowering, or the vapor pressure decreases with an increase in the number of solid particles. Like for example, if you look at this equation from this mole fraction, remember that we said colligative properties depend on the number of solid particles, not solvent. Look at this equation. This is numerator. And of course, this is the denominator. So in this case, if you now look at from this equation, you can see that the number of moles of solid particles is at the denominator. So it means that the more you increase the number of solid particles, the more you increase the weight of the denominator. So it means that the more you increase the weight of the denominator, meaning that the more you decrease the mole fraction. Because as you are increasing the values at the denominator level, of course, the function, which is the fraction, which is the one fraction of water here, will be decreasing. So that is why generally, as you increase the number of moles of solids, then you decrease the vapor pressure will be decreased. So an increase in the number of moles of solid particles leads to decrease in the vapor pressure. So this is the formula that is used in calculating vapor pressure of a solution. So let's also just look at some examples and so. Okay, so let's now look at this example. Calculate the vapor pressure of pure water at 20 degrees centigrade in a solution purified by dissolving 10.0 gram of non-volatile sucrose. And the formula for sucrose is C12H22O11 in 100.0 gram of water. The vapor pressure of pure water at 20 degrees centigrade is equal to 17.54 gram. So it means that now, by looking at the question says that let the vapor pressure of pure water at 20 degrees centigrade in a solution. It is a solution. It means that we are going to find the vapor pressure of a solution. Solution is unknown. And then the partial pressure of a solvent, or the pressure of a solvent, which is pure water here, the vapor pressure of pure water is given clearly as 17.54. So it means that the vapor pressure of the pure water, the vapor pressure of water is equal to 17.54. And then, of course, the mole fraction is missing completely, so it means that we have to calculate the mole fraction of water. And how are we going to calculate the mole fraction of pure water? First, remember the formula that can fit into this is this: the mole fraction of water is equal to the number of moles of water divided by the number of moles of water plus the number of moles of water plus the number of moles of sucrose, because here is sucrose, so divided by the number of moles of sucrose. And of course, we don't have the number of moles of water, but how are we going to calculate the number of moles of water? First, we are going to take the mass of water. So the mass of water is 100.0 grams. So the mass of water is 100.0 grams. It means that now the mass of water is equal to 100.0 grams. And then, of course, we need to know the molar mass of water. So how are we going to calculate the molar mass of water? To calculate the molar mass of water is simple. So we have two molecules of hydrogen in water and 1 molecule of oxygen. So since we have 2 molecules of hydrogen, we are now going to say 2 times the mass of hydrogen is 1. So we write 2 times the mass of hydrogen, then plus, open brackets, we have 1 oxygen. And the molar mass of oxygen is 16, so we are now going to say 1 times 16. So 2 times 1 is 2, plus 1 times 3, then we have 18 gram per mole. So therefore, now to calculate the number of moles, of water, we are now going to say 100 from 0 divided by 18. 100 divided by 0 divided by 18. You write the answer here. And then we now have, so then the next is to calculate the number of moles of sucrose. Is to calculate the number of moles of sucrose. And of course, the number of moles of non-volatile sucrose is 10.0 grams. So we now have 10.0 grams. We now have 10 divided by the molar mass of sucrose. And of course, the compound or the chemical formula for sucrose is C12H22 plus 11. So I think it's simple. We are now going to say how many carbon do we have? We have 12 carbon times the molar mass of carbon is 12. And then we also have hydrogen. We have 2 hydrogen. And the molar mass of hydrogen is 1. And then 11 oxygen. So we are now going to say 11 times 16. So when we now take this and we add everything together, from this, we are now going to get the molar mass. We are now going to get the molar mass of sucrose as 352. So therefore, the molar mass is 342 grams per mole of sucrose. So therefore, now we are going to say the number of moles of sucrose is equal to 10 divided by 342. So 10 divided by 342, we are now going to get, so now the number of moles of water, we have 100 divided by 18, we have 5.5 moles. And then for the number of moles of sucrose, we have 10 divided by 342, we have 0.029 mole. And this is the number of moles of sucrose. So it means that now to calculate the mole fraction of water, we are now going to say the number of moles of water divided by the number of moles of water plus the number of moles of So that the number of moles of water is 5.56 divided by 5.56 plus 0.029. So if you now take this and if you now take this and you divide it by this, you are going to have 5.56 divided by 5.529. So therefore, if you now take this and you divide it by this, you have 1.0056. So therefore, if you need the final rate of the solution, the fraction of water times the mole fraction times the final rate of water, which is equal to the mole fraction of water is 1.0056 times the vapor pressure of water is 17.4. So we now multiply this and whatever we get is our final answer. So this is how to calculate the vapor pressure lowering according to qualitative properties of a solution. So let's try this. It's a similar question to the previous one that we just solved. Calculate the vapor pressure of water at 90 degrees centigrade for a solution by dissolving 5.0 gram of glucose in 100 gram of water, and the vapor pressure of pure water at 90 degrees centigrade is 524 torr. So let's do this calculation and put the answer at the comment section. Okay.